So in this video, I want to show that our recurrence that we basically had come up with from looking at the solution to towers of Hanoi is actually the same thing as our guess for what is the closed form version of it. Again, right, the recurrence isn't very useful to us because basically whenever we want to evaluate for a specific n, we have to basically do all these kind of recursive steps where we go backwards, backwards, backwards. Really what's more useful is for us to have a closed solution, right, that we can basically put in our value of n and directly compute what is the number of moves that are required. So the stuff we've basically discovered already is this stuff over here. So this is basically our known truth. There's this little bubble over here with a hem over there as kind of a side note. We're kind of just taking this to be true, right? If there was an issue in the way we analyze our code, maybe this wouldn't be true. But we're just going to basically assume that our initial analysis or our initial recurrence is accurate. So there's two parts to the recurrence. First of all, f of 1 equal 1. So basically, for the very small tower containing just one disk, if I want to move it, well, that takes just one move. So pretty simple. Second thing there, right, was more complicated, is the f of n, right, the general step. So f of n equal to f of n minus 1 minus 1. So this is the recursive part, right, where the number of moves required to move a tower of size n is based on the number of moves required to move two smaller towers, right, two size n minus 1 towers. Okay, so that's what we have, and then based on our guesses that we made before, we think that the closed loop solution looks something like this, to the n minus 1. And so our goal basically is to show that for any n, right, any size tower, these two things will always be the same. Initially, right, we know that these are the same in terms of just what we plotted out. So you think back, we had basically this graph. We started at 0, we went up to something like 16, and we just evaluated these two functions for each of those two, for each of those values of n. And they look the same. But the problem is, how do I make sure that they're always the same, right, forever that they will match up? Well, we can do that using induction. Right, so the idea of induction again, right, is so that some property holds true for every value of n. Right, basically we're asserting that something is true for every element of a set. Here the set that we're looking at is a set of natural numbers. So we're starting at 0 basically and going up by 1. And we want to show basically for any possible tower, right, that's maybe our set is tower sizes, that this property holds, that these two things match up. That's what we want to assert, and we want to assert that for basically any size of tower, these things will hold, not just the size of towers that we have listed in our table, right? We want to assert it for everything. Okay, so how do we get there? Well, first thing we got to do, and induction generally has two parts. First of all, right, we need to decide basically what n is bound to. So we're bounding n to starting at 1 and going upwards. And then, we could have also started at 0, right, but it doesn't really make sense to move an empty tower. So we'll start at 1, so we'll use natural numbers. But we need to basically decide what variable, right, we're iterating over, if you would, right? What is the set that we're going to prove things from? So that here is just natural numbers. I'll make a note that this variable n, right, basically the size of towers, is coming from that set. It's a natural number. Now, for induction, we have basically two parts. First of all, we need to start with the inductive case, which is basically like what is the simplest thing I can show to be true, right, a starting place. And then if I have that, then what I want to do is go look at the inductive step, which is going to say, okay, given that a particular that this property holds for some k, right, for some tower size, that it'll also hold for one larger tower, right, tower size plus 1, k plus 1. That's the inductive step. That lets us basically grow and eventually touch each of the natural numbers, right? Because if my property can be shown true for some number like 10, well, then that rule would let me show it true for 11. And if it's true for 11, then it's also true for 10 by using that same rule. So that rule, right, that inductive step, basically lets us span all the natural numbers and assert that our property holds for everything. This is rather nice because if you think about it, well, natural numbers, there's a accountably infinite number of them, right? And we're going to basically show that this property holds for all of them, right? Even though we just do it in this one case, it'll work for all of them. All right, so looking at our two steps, first thing we need to talk about is the base case. So in terms of the base case, basically what I want to do is I want to show that what I'm trying to prove, right, basically holds true at some starting place. And the starting place I'll go with is actually n equal 1. And so n equal 1 be my base case. And what I would do is basically put that value for n into my formulas. So I know, of course, right, that f of 1 equal 1. So over here, basically, I can write this stuff here, f of 1 equal 1. And then I'm trying to assert, right, that that'll be equal to the other formula, the formula that I guessed. So that's this formula here. So this basically comes down over here. And I've basically just set n equal to 1. So there's two parts here, right? So this stuff over here comes from this. This stuff over here comes from the one above. And if I evaluate those, right, I'll find out that I get 1 and 1, right? This is obviously true. So at least for that base case of n equal 1, the property holds, right? Those two things are the same. So when I say property, I'm really meaning here those two formulas are equal, right? I mean, we could just be asserting many facts, right? We could be asserting something like, oh, the number of disks in the tower is odd or even or something like that. But the property we want to investigate is just to check to see whether those two things are equal, right? Whether my guessed formula and my formula that I came up with based on the code give me the same result. So for here right now, I've basically shown that to be true. Okay, so let's now take a look at the inductive step. So the inductive step, basically my job is to say, okay, this property holds for some k, and that will imply that it holds for some k plus 1. And that property being, of course, that those two things are equal. So here I get a little bit of somehow of magic. So I am actually allowed to assume that case k is true. So this little bit here. So this is basically coming from our guess, right? Our guess was over here up top, right, for our original f of n. Now we're saying is that inductively, well, in terms of induction, what we'll assume basically is that this holds, right? So we're going to be given that case k holds, right? So we're given this as true. Even though we haven't really done anything, we're just going to assume it. That's something there that's basically available for us to use algebraically. Okay, and really the only difference there, right, is I've substituted in k for n to basically represent that this is kind of your inductive hypothesis, right? This is what you're allowed to assume. So using that kind of fact, right, we want to build from that. We want to show that this is valid as well. Basically, we want a way to derive f of k plus 1 from f of k, right? We want to link those two things up, right? Get the ability to basically step forward and say, this is true, this other thing is true as well. So how can we get there? And actually, maybe before I get there, what is our end goal? Our end goal is really something like this. We want to recover the following formula. We want to recover f of k plus 1 equals 2k plus 1 minus 1, right? That's what we want to recover. So we want to get from this initial k, f of k to f of k plus 1. Right? We want to move between those algebraically, not kind of making any assumptions and just using the information that we have. So that's kind of our goal. So we start with f of k. So what can we do? The first thing we can do is actually think about using basically our original formula, right, the recursive one, the recurrence, to write an expression that basically computes f of k plus 1, right? Because that initial recurrence stuff up top, right, those two ways to compute f of 1, f of n in terms of recurrence, those are going to be valid no matter what, right? We already took that to be true. That is our stuff that we get basically forever, right? It's free for us to use. So what I could do is I could think about writing the expression for f of k in terms of that original rule. And so that's basically what we've done here. We have basically a few things going on. I'm shifting a little bit, right? The original rule is written in terms of f of n. Now we're basically saying n equals k plus 1. So we're doing a substitution in a couple places here. And we end up with this thing here. So this is basically my formula for f of k plus 1 in terms of that original formula. And then what I have, right, is I have that recurrence going on. And that recurrence is normally referring back to a smaller value of the function, right? So here it's referring back to f of k, right? So f of k plus 1 is computed from f of k. But here, right, this isn't really what I want, right? Again, think of my goal, right? My goal is to get to this thing over here where I have my expression that's a closed form expression. It doesn't have any functions being called or referred to. So if I turn it bound to the line that I'm manipulating, this f of k, what I can actually do is I can actually substitute in this over here. Right, so I'm substituting in what I assume to be true. So that brings me basically to this line right over here. So in a sense, what's happened between these two lines is I said, okay, I want to get from k to k plus 1. I'll actually start with the thing that I'm allowed to assume, right, that my formula or my property holds for f of k, and then I'm somehow going to grow it, right? I'm going to move it forward using my original formula. Because for sure that original formula will work, right? And the whole purpose of that formula, right, the actual line up here, this thing, right, really, mechanically, what it's doing is it's evaluating some value for a tower based on a smaller tower. So it's linking together, right, a tower of size n with a tower of size n minus 1. And so what I'm doing over here, right, is I'm trying to, at the bottom, prove that the case k implies the case k plus 1. And so that original function I have, basically that's the mechanic I have to do that, right, to jump from k to k plus 1. Because I don't have anything else that can get me between those 2 points. So I start with what I assume, right? I assume that property, that expression, right, holds for f of k, and I use my original known good formula to move up by 1. Okay, so we're kind of combining two things here, right? We combine our assumption with basically the way we stepped forward in the original recurrence. So that gives me this line down here. and this line down here, all of a sudden I have eliminated f of n. And so I have this f of k plus 1 being equal to 2 of 2 to the k minus 1 plus 1. So I have that. The problem is I'm not really done yet. So that's kind of a full expression there, but it doesn't look just like that, right? This thing over here, our goal. Really what we want is we want that exactly. And the reason why I want that exactly is because this over here, this stuff, looks exactly like what we were allowed to assume, that f of k equal to k plus 2 to the, f of k equal 2 to the k minus 1. Right? These two things look exactly the same, this f of k and this f of k plus 1. The only difference, right, is that there's a plus 1 basically where the k is. Right? So whatever it is, the expression that we produce should look exactly the same except for that plus 1 being added onto there. Right? If there's still other kind of things to algebraically manipulate, we got to take care of them. We can't just leave this be and say, oh, hey, I wrote f of k plus 1 with stuff that's not a recurrence. Right? There's no f of n on the right-hand side. I can't stop there. Algebraically, I need to carry through and make sure that I match my goal. Right? My goal is to basically regenerate this f of k, but with the plus 1 added to that k. Okay, so from this point, it's just algebra. So I have here, right, my 2 times 2 to the k minus 1 plus 1. So I expand basically the coefficient. So I multiply that in. That gets me basically 2 to the k plus 1 minus 2, right? So just imagine you're distributing, right, in there. So your minus 1 is times 2, gets you minus 2. And then you're doing basically 2 times 2 to the k. Well, what happens is that power, right, because the coefficient matches what your power is on, the power will absorb the coefficient in front. So we end up having 2 to the k plus 1. Almost done there, right? Then we just basically do the addition, add that 1 to the negative 2, and we get over here 2 to the k plus 1 minus 1. So in this case, right, here we've basically managed to carry through, and we've recreated the original formula that I started with, but with basically that plus 1 now in there. So that's it. We're done, right? The idea there, right, is basically we're recovering that f of k, right? We want to show that starting with the assumption that f of k is valid, right, that expression holds, then we can show the case k plus 1 will hold, right? And we would do that basically by recovering the original formula, but with that slight alteration of that plus 1. And the way we got there, right, the way we got there from f of k to f of k plus 1 is basically by using my original formula, right, or my original recurrence to do that little step forward, right, to basically do the work of making it a prediction, right, for a tower that's 1 bigger. And that's a legit step for us, right, because we know that recurrence is our assumed truth, right, and so we can use that to basically take a step, right, and say, okay, the k plus 1 step case is also true. So putting this together, basically what we have, right, is we have our base case and our inductive case. And we have our base case and our inductive step. So base case says, hey, these two formulas match up for k equals 0. Great. Then we have our inductive step, which says, okay, if those formulas hold, right, if the property holds for k, then it'll hold for k plus 1. Well, there we go, done, right? So we start at 0, plus 1 it, get to 1, plus 1 that, get to 2, plus 1 that, get to 3, plus 1, get to 4, and so on, right? So putting these together, basically every single value of n, right, all the natural numbers, these two things will be the same, right? We proved that. And so now we know that our two formulas, right, our guess and the recurrence we got from the code are the same thing, right? So that is an accurate guess, right? We've proved that they're the same, so now we're good to go. Some final remarks here about the f of n. So basically what we've done, right, is we've verified that we have a closed solution, right? We had a solution before, but the problem was it was recursive, right? It was a recurrence, so it was expressed in terms of itself. It's very hard to evaluate, but now we have what we want, which is a closed form or a closed loop solution to it. Given that we have f of n, right, which is a growth function, right, it's going to exactly compute for us the number of moves that are required. We can actually now think about maybe computing the big O or even the tilde of it or whatever we want of it. So maybe think for a second. Given this function here, this f of n equal to the k, to the n minus 1, what will be the big O order of that? And then what will be the tilde of that? So maybe think for 1 second. Okay, so big O for that is going to be, it'll be big O of 2 to the n, which is actually something that we haven't really seen before. Before we've seen things like O of n or O of n squared, but here this is O of 2 to the n, right? So this is an exponential time algorithm. The problem with exponential time algorithm is it's something that'll basically take forever, right? So as I increase n, right, the number of disks, this will grow very, 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 very quickly, right? It'll grow exponentially quicker. Just doing, going from 10 to 11, right, for a size of n, all of a sudden doubles the basically the number of moves that are required. And this is very bad, right? This is something basically for any reasonably large number of n, we're just not going to be able to compute. It'll simply take too long. Then what about tilde? Tilde for this is going to be also 2 to the n. So remember the difference between big O and tilde was that big O doesn't drop the coefficient in front. Instead, we just leave it there in order to be more accurate. Okay, so that's kind of our growth function right up top. Those are our big O and tilde analysis of it. So pretty good. We now have this idea of how this algorithm will work.